So we've been looking for area under curves, and we've been using this notation here where we add, or the summation of all the areas of the rectangles that we can fit under the curve. And then when we put a limit in front of it going to infinity, then we're saying that's an infinite number of rectangles and we're finding the true area under the curve. This is another way to write all of this, and an easier way to write it. Here, this is called the integration sign. And we have got a to b. That's our upper and lower limit of integration. And that's the same thing that we've been looking at when they give us an interval a to b. So a is just your starting value, b is your ending value, and then really the rest of it is the same. Our example that we're looking at first is example 2. They want us to take this curve and they graphed it for us. And they want us to evaluate the sum. First, we're going to do it the old way and have right endpoints, just 6 rectangles, which they drew for us. And then we're going to do it using the new notation and find the true area under the curve from 0 to 3. We can see that a lot of the rectangles are below the x-axis, and these are going to give us negative area. And then the rectangles above the x-axis are going to give us positive area. So if we add these together, it looks like we're going to get a negative value. And that's just telling us where the majority of the curve is. The majority of it is below the x-axis. So let's start with part A. We've got this function. And let's write that down. And we want to find the width of our rectangles. So we're going to find change in x, which is b minus a over n. And they gave us 3 and 0 and 6 rectangles. So the width of my rectangles is, 1/2. Let me rewrite that, 1/2, or 3 over 6. And so if I think about my 6 rectangles with a right endpoint. So there are my 6 areas. Each of them has a width of 1/2, and I just need to plug in x values and find the heights of these rectangles. So let's make a list of what x values we would plug in. The first x value, if I'm using a right endpoint, is going to be 1/2. If the width of the rectangle is 1/2, then it's going to end at 1/2. The second rectangle would be another width of 1/2, so 2 halves. Then another width of 1/2 would be 3 halves. And then 4 halves. And then 5 halves. And then 6 halves. So those are the x's that we're going to plug in to our function that they gave us. And the function they gave us is x cubed minus 6x. So if you plug in 1/2, you get negative 2.875. If you plug in 1, you get negative 5. If you plug in 1.5, you get negative 5.625. If you plug in 2, you get negative 4. If you plug in 2.5, you get 0.625. If you plug in 3, you get 9. And again, I'm plugging everything into this function. Each of these x's gets plugged into this function. And these are the heights. So my first rectangle went below the x-axis, and so did the second one, and so did the third one. I should have spaced these out better. And the fourth one, and then they started to go above the x-axis. And so if you multiply each of these together and then add up all the answers, you end up getting an area of negative 3.9375. So that is part A using 6 rectangles. Now part B, we're going to find the true area under the curve because we're going to take the number of rectangles to infinity. So B, let's start a new sheet of paper. B, they say 0 to 3 of x cubed minus 6x dx. So what this says to me is they want us to do the limit as n approaches infinity of the summation from 1 to n of f of x sub I times delta x. So the sum of all the areas, and we're taking the number of rectangles to infinity. So we can find our delta x. We already did it on the last one, but you would do the upper limit of integration minus the lower limit of integration divided by n. And the ith term will just be 3 over ni. And we can find that by making a list and seeing what happens. And you're just multiplying the index by 3 over n. So I times 3 over n. So this is what we plug in here, and 3 over n is what we plug in here. So we're going to rewrite this as the limit as n approaches infinity of summation 1 to n of, now my f of x sub I, this is f. This is f. So I'm going to plug x sub I into that. So I've got 3 over ni cubed minus 6 times 3 over ni again, because that's the x value, and then dx, 3 over n. And so now your goal is to get all the constants and the letters in front and then isolate all the i's. So the first thing we're going to do is bring that 3 over n in front. And I'm going to go ahead and simplify these. So that's going to be 27i cubed over n cubed. And then we're going to multiply these, and we get 18i over n. And then I'm going to split the summation into two summations. So I've got 3 over n sigma 27i cubed over n cubed minus the same sigma 3 over n sigma 18i over n. And then we're still trying to get the i's by themselves. So we're going to bring the 27 over n cubed in front, which is 81 over n to the fourth summation I cubed, minus, bring your 18 over n in front, and you get 54 over n squared. And now we've got our i's isolated, and we can plug in the formulas for those. So sigma I cubed is n, give him his phone back, n plus 1 over 2 squared. And then we've got sigma I is n plus 1 over 2. So now the sigmas are gone. The sigma I cubed became that, and the sigma I became that. And now if you simplify these, so if you distribute your n and square it, then you end up getting n to the fourth, 2n cubed, n squared over 4. And you get, if you distribute your n squared plus n over 2. And then we're going to distribute 81 and distribute negative 54 and multiply the bottom. So you get 81 n to the fourth, 16 or 162 n cubed, 81 n squared over 4n to the fourth, minus, distribute your 54, so negative 54 n squared minus 54 n over 2n squared. And then when we find the limit of each fraction, the limit of this one, since the 4's match, is 81 over 4. And then here, those match The n squareds match, so negative 54 over 2. And together those make negative 6.75, which would be the true area under the curve.